ground rules and my intro. I'm going to now introduce Professor Erich Muller from Imperial College London. Erich is the Professor of Thermodynamics, which was never my favorite subject, so I'm hoping I can learn a lot today, at the Chemical Engineering Department at Imperial College. He tells me he's got over 30 years experience, he doesn't look that old, in describing complex fluids and interfaces at the molecular level. He's involved in a number of BP ICAM projects, notably ICAM 10 and 15, leading the modeling work in there. It's been with us since, I think, the beginning, Erich, of ICAM. I'm not going to say any more, but just to let Erich start and tell us a little bit about the molecular simulation of fluids. Over to you, Erich.
Okay, thank you. Thank you, Sheetal, and thank you for the audience we have. We have also a full house here at Imperial, so it's very pleasing to see this. I'll start this talk, as I've started others, mentioning a comment that Richard Feynman, for the younger ones in the audiences, you probably don't know that he was a Nobel Prize winner in physics. And he made during his talks he made a very nice open question, and he basically says, what would happen if for some strange reason all of the scientific knowledge was wiped out of humanity, and you had the chance of writing on a piece of paper just one sentence that could be passed on to the new generations of humans or whatever was left in the world? What would you write in that single sentence? What could you do to write something that was so physically meaningful and could convey enough information for them to start on the right track? And of course, there's many people joke on what they would write, you know. But if you think of it, it is quite a difficult task to summarize things in just one sentence. And actually, his proposal for that sentence was basically the atomic hypothesis, or the atomic fact, or the fact that all matter is made of atoms or little particles. And if we know and we understand the behavior of these atoms and we study them, we can obtain a lot of information about basically everything that surrounds us, including even aspects which seem quite unusual. So in that sense, this talk is going to talk about understanding the behavior of matter through the molecular modeling, especially at that atomistic scale. But before that, I just wanted to mention that this is a rather introductory talk, and I apologize for those who want the hardcore science, but there's a limit of the amount of information that we can put in one hour. So I'm going to give first an outline on what simulation means and what people understand as simulation, and then I'm going to start focusing on the most basic form of molecular modeling, which is molecular dynamics. What does it mean? What can we do, and what can't we do with it? And then start from there, noticing that there are improvements that we can make in terms of, for example, speeding up things and using coarse-grained models, or even better, linking up with other scales of modeling as multi-scale modeling. As Sheetal already mentioned, I will be using some examples taken from our recent work in ICAM 10, ICAM 15, and with some EPSRC-funded projects. So the first question is what is simulation? And simulation means different things for different people, and that's what we have to put the record straight to start with. For the classical chemical engineer, simulation will mean looking at things in spreadsheets and modeling plants and chemical plants with the use of computers. For a hardcore chemist, computational chemist, the only form of computer simulation is to do quantum simulations and understanding Schrödinger's equations of motions. And between those two extremes, we have a wide variety of different scales of understanding and matter. What this slide tries to show is the fact that we can span several length scales and several time scales with different types of modeling techniques. And I'll go through each one of these with a little bit of detail, just to describe what these different scales are and what these different lengths and time scales actually mean. So as I said, the first one is quantum mechanics, which is probably the most elegant one. It's an ab initio technique. Basically, it doesn't need anything to start with. It's essentially an exact numerical solution of Schrodinger's equations, and as such, it's extremely computationally heavy. Up to now, we can only do that for only a few simple systems, and rather interesting from a theoretical point, but probably not too much from a practical point of view, or maybe an engineering point of view, if you want to look at it that way. However, we can make a few simplifications to quantum theory, and basically one of them carries on to what is known today as density functional theory. It's extremely popular technique. Basically, it can allow us to understand the behavior of the electron clouds around a fixed nucleus. And we can talk now about looking at maybe hundreds of atoms and even thousands of atoms if you have the correct hardware. There's two issues with respect to DFT particularly. The first one is it's quite curious, but in the case of DFT, you have to define some wave functions for the electrons. And it just happens that if you want to increase your precision, going into more complex wave functions doesn't necessarily guarantee success. So it comes to a conundrum in which you don't really know how to improve your model, because making it more complex doesn't necessarily provide a better solution. So you're stuck with a crucial unknown, which is how to improve on my answer. A second one, probably not also equally important, but maybe has a closer solution, is the fact that dispersion interactions, which are for most engineering applications crucial in terms of forming condensed phases or self-assembly, are not well taken into account with simple DFT, and quite complicated strategies have to be taken into account to account for this. As an example taken from ICAM 15, we were looking at the absorption of toluene on cementite, which is a solid surface. And in this case, you have toluene as a dark painted molecule. And the type of information that we can extract from these DFT calculations are, for example, the absorption energies. And in the top right cartoon, you see what the absorption of a toluene molecule is lying flat on the surface in the order of 200 kilojoules. And on the bottom two figures, you have the absorption of two molecules or dimers absorbing on the surface. And two things are, for example, immediately obvious from here. One of them is that the absorption of the fluid-fluid interactions between two toluene molecules are much smaller than the interactions of the solid, because the dimer interacts with around 200 kilojoules per mole, 266 kilojoules per mole, while the single molecule has around 200 joules of absorption energy. So the interaction between the two fluid molecules is an order of magnitude smaller than the solid interaction. And the other one is that orientation does matter, and there is, again, a significant difference between the fact that the molecules lie flat on the surface and lie vertically. Of course, much more information can be gathered from this, but I'm just giving you an example of the size and the scale of the classical systems that we explore. Obviously, this is probably too little to study, for example, condensation of a liquid in a surface, and much too smaller if we want to see self-assembly or bigger effects. So we have to turn into a higher scale, a coarser scale, one in which we can see a little bit more of, lose a little bit of detail, but attack a lot larger systems. And this corresponds to the avenue of atomistic modeling. Here, atoms and molecules are taken distinctively as points of mass. Usually, for example, a CH3 group can be considered as, or taken as a sphere. In the cartoon on the top right-hand side, you can see absorption of water on an oxygenated surface, for example. And now you can immediately see that we're talking about larger number of particles that we can study, because the interactions are now much simplified. Instead of looking at the full interactions between the molecules as given by quantum mechanics, we take basically an empirical force models which somehow fit that distribution, that energy distribution, and we use them directly in our calculations. We will deal a little bit more on atomistic model in further on, but I'll give you here an example of the types of things that we were looking at. In this case, we have a water flowing through a sheet, the graphene sheet, which has a perforation in the middle. One of the water molecules is highlighted for you to try to see it, and there's a flow of water, believe it or not, from your left-hand side to your right-hand side. The immediate thing that you can see is that it doesn't flow like the water that off your tap. You see that there are interactions between molecules, and these interactions are the ones that mediate everything. The other one is finally water is trying to just push through the hole, and we all have to think together hard. If we think together hard, we'll probably see that water molecule just finally make it through and get to the other side. Okay. So what I wanted to point out also with this slide is that the hydrodynamics is not captured by this. The scales are too small. We're looking at atomistic scales. We're looking at molecules in a small system. And there's lots of details which are probably unnecessary. We modeled a lot of the water-water interactions. We modeled a lot of things which were not of real interest. And we might have been able to get this picture faster if we had thought about coarse graining. Coarse graining refers to deleting some of the atomistic detail in our model, which for some reason is slightly irrelevant. The example shown on the top of the slide is of a big macromolecule, in which made out of different benzene centers connected together to form something like a hollow ring. And this is basically a liquid crystal. Modeling atomistically would take an enormous amount of computing power to take into account all these atoms and all the interactions between these atoms. But by simplifying, we're taking a coarse-grained approach on this molecule by lumping together different atoms in a single bead. We can then start seeing, for example, the behavior of the system. This particular system produces a smectic phase, or a liquid crystal phase that has structure, with the rings interpenetrating one against the other, forming some nice, beautiful layers. And this, of course, would be impossible to see in the time scale of an atomistic simulation. When we reach these scales of coarse graining, you probably recognize that we're very far from the quantum level where we had some assurances that we were doing things correctly. So there is a risk that when we go up these scales and we integrate every time, and we smooth, and we might be throwing away some details which are important, and we might just be losing a little bit of the physics. So the risk of GIGO is clear here. The garbage in, garbage out in our simulations. We have to be very sure at this level that we're doing things correctly. And again, I'll discuss a little bit more of that later on when we talk about coarse graining. I'd like, again, to show you another example in terms of the use of a liquid crystal. In this case, it is a T-shaped liquid crystal formed by a rigid central core, which is aromatic, which basically doesn't move. It looks like a pencil. And at both ends, we have polar groups, groups which like to form hydrogen bonds and like to bond with each other. Laterally, on this molecule, there's a fluorinated chain. And curiously, this fluorinated chain, or this fluorinated part of the molecule, hates the other parts of the same molecule. So it's in terms of a molecule itself, it's a very strange one. It hates itself, and so in some way, but it likes itself in other parts. If we let this liquid crystal evolve in time, if we do the modeling of the evolution in time, we see that the liquid crystal will self-assemble. And you can start seeing here in a plot of the order parameter as a function of time how it has slowly started to form a distinct phase. And suddenly there's a jump at this point, and immediately it forms a hexagonal honeycomb structure. So a tubular, two-dimensional structure, completely self-assembled. And this, of course, corresponds with what we see from X-ray diffractions on this exact same molecule. What is interesting to note, for example, is that before we did these simulations, people tried to do these simulations with fully atomistic models. And they couldn't see the self-assembly, and they couldn't prove what was going on. And by looking back at their work, it just happened that they were not spanning time, a long enough time. They're spanning at the most a few nanoseconds of simulation time with atomistic models. And if you can see from the graph, at 5 nanoseconds, you basically don't see any ordering in the system. So you really had to span long time scales, which was something that could be done by simplifying the model and performing longer sizes and longer times. If we keep going up in the ladder of knowledge, we have a continuum model. So in the case of continuum models, now the atomistic detail is completely lost. We're now looking at the solution of basically Navier-Stokes equations and energy equations in a continuum phase. This is of course accurate in as long as we have the correct thermodynamics and transport coefficients input to it. So it's not an ab initio situation. It's a situation which simply follows what we somehow know, usually experimentally. Lattice-Boltzmann techniques, for example, fall in this category. And again, in the case of lattice-Boltzmann, there is a speed up in terms of having a continuum, the continuum being discretized in time, and the solutions of these mass and energy equations being solved in a lattice rather than a continuum. For those in the audience in the oil and gas industry, reservoir simulations also fall within loosely within this category. As an example, I'd like to show you one thing done in the group of Omar Matar here at Imperial College, which is the Asphaltene deposition on hot pipes. In this case, we have a crude oil which has some asphaltenes in it, and when passed through a hot pipe, the temperature of the walls will start precipitating the asphaltenes and eventually coking them. And eventually the pipes will start clogging up, much in the way as cholesterol clogs the pipes of the arteries of a normal human being. The CFD is very appealing. It is physically and visually appealing, and you can actually see what's, without too much explanation, what's happening in the system, and you can probably understand it. In that sense, it's a really powerful tool. But it's important to recognize that it does only what you tell it to do. Hence, if in this case, for example, we have to give it the rates of deposition, we have to give it the kinetic models, we have to give it all that information, which in principle is unknown. So you have something which is very detailed, but you have to give it a lot of information for it to be realistic. At the end of the spectrum, and I'm not going to talk too much about this, is the classical chemical engineering point of view, in which we have a spreadsheet and we can take a very large process and break it up into small unit operations which are connected through mass and energy balances. This is usually not considered molecular modeling. However, I included it because there is a brand new tendency to try to link these big scale operations with more molecular understanding of matter, and even with the smaller scales of molecular modeling as we do right now. The area it has been coined by our group as molecular systems engineering, and is an emergent field where this types of linkages happened. It's very difficult to do, but on the other hand, it's quite exciting because it would allow us to take some of the things which are only seen by academics into probably what some people would call the real world or the academic or the engineering world. So let's go into the core of the talk, which is the modeling at the scales that at the atomistic scales. The first one and the easiest one is the molecular dynamics. And in molecular dynamics, we're basically solving Newton's equations of motions for all particles. It's an n-body problem, but it's a relatively simple from the conceptual point of view. So we'll go through it with a little bit more of detail. What we're basically doing are computer experiments. And for those that come from a lab, you'll recognize that in a lab, every experiment has basically 3 parts to it. There's a preparation of the material, there's a connection of that sample to something, that's to an apparatus which is going to measure something, and there's a third part which is a measurement of the property or the analysis of what the result came. And the molecular dynamic simulation is very similar to this. Basically, it's a pseudo-experiment, although we don't like to call them that way, but definitely there is a parallelism. And basically, there's three parts to it. The first one is to select the model that we want to study and choose a force field for that model. The second one is to place in an instrument, in this case it's our computer, and basically and our software. And basically we solve Newton's equations of motions for these particles, and until we see that the system equilibrates or reaches some steady state. And finally, at the end, we do something with that. We calculate a certain property, we average a property over time, and if necessary, we repeat the experiment several times to get better statistics. So, taking again an example from the ICAM projects, one of the projects is on the deposition of carbonaceous substances on surfaces. And amongst them, one of the interesting compounds are asphaltenes. Asphaltenes, for those in the audience not clear on this, are large organic molecules which appear in crudes, which, due to their size, given some correct conditions of temperature, pressure, and composition, precipitate or separate out of the crude oil, causing enormous problems in production. The problem we have, for example, in this case, is that the object of study, basically the molecules, are unknown. In chemical and biological sciences, we're very clear on what what we're studying. We're studying a certain molecule, we're studying a certain protein in a certain very well-defined system. In this case, we only have an idea of what the basic chemical composition of asphaltenes are. And by several different experimental avenues, we have some clues on what these molecules look like. But basically, we're stuffed with the problem that we don't know what we can't describe a molecule. So in this particular case, out of many millions of different possibilities, I'm going to keep talking about asphaltene C, which is on the right-hand side of your slide, for no particular reason. Simply because at some point, we just have to choose one and start looking for one. The second thing we need to do is describe the force field, or describe the energetics between the different parts of this molecule and other molecules. Here we struck luck, and in this case, there are several force fields available, many dating back to the 60s, where basically the start of modern molecular dynamics simulation it can be traced back to. Several of these force fields are available, and I might say not thanks to us, but basically they have been imported from biochemistry, where they have been really very, very successful. They're based on a very clear idea of group contribution, basically that different groups of molecules, for example a CH3 group in a given molecule, is always going to behave the same way. And we can transfer that CH3 group, for example, from an alkane to a protein or to a smaller molecule. The force fields are rather simple in their constitution. They're based on they're based on dispersion forces between two types of molecules. They're based on point charges between groups of molecules, and a set of rules with respect to the bond stretching and bond bending and bond torsion. And most modern force fields have basically this structure, which can be attributed basically to the 3 Nobel Prize winners of 2013. Actually, they won the Nobel Prize because of this contribution to this field. So now we have the description of the molecules, we have the force fields, and then the next thing is how to solve these things in a computer. And as I mentioned, it's as simple as solving this apparently innocuous equation. The force equals the gradient of the potential, and the fact that, of course, the force is the acceleration of the second derivative of the position with respect to time. So basically, we have one equation for each molecule or atom in the system, and we have a set of coupled second-order differential equations. So that sounds like a big task, but in general, it is rather repetitive. It is simple from the math point of view. It is, however, a very repetitive task. It can't be solved exactly, so it must be solved discretely by discretizing time and solving for these equations of motions in delta t's of time. Here you have now a simulation of that asphaltene molecule now in toluene. We have 27 asphaltene molecules for around 7% weight. And at these conditions, the system is unstable in the sense that it precipitates, or the asphaltenes are expected to precipitate. And you can see that they're starting to stack one on top of the other, like cards, like deck cards. And if we give the system time enough, you'll actually see the whole system cluster into one big cluster. So this simulation you're seeing here has many of the elements erased from it, so you can actually see something. All the solvent, for example, is deleted just for observation purposes. And you're only seeing a small snapshot of the whole simulation. The whole simulation took half a nanosecond of time, of real time. For real, I mean for molecular time. And I call it here a heroic simulation. It's almost an order of magnitude larger than the largest simulation reported in the literature. And even then, I'll convince you that even then this is not large enough. It took the poor postdoc over a month of CPU time just to get this amount of information and the part of the movie that you're seeing. In the next part of a simulation is then to understand what's going on, to actually measure something and to see what we're obtaining. So in this slide, you have the behavior of the system in two solvents, in toluene and heptane. In toluene, the system is soluble. In heptane, the system separates into two phases. In red, you have the first 100 nanoseconds of the simulation. In green, you have the last 100 nanoseconds of the 500 nanoseconds. You see that in toluene, nothing is really happening. From at 100 nanoseconds, we have a distribution in terms of the cluster size, which is the variable we have at the abscissa. Molecules just cluster in pairs, in trimers, etc., but they don't advance much more, and there is no further clustering. In heptane, on the other hand, you see that the simulation, the picture you saw, the movie you saw, was for the red curve, and you see that there is a clustering. If we had left that 5 times longer, you would have seen that the clusters would be larger and larger and larger. This is by far the largest simulation we can do, and it's still pathetically not enough. It's too small a system. It's a simple solvent, and the time simply is pointing to us that we really need to just explore larger time frames. So did we run in the fastest computer available? Well, yes, we did. Those simulations were run in the BP cluster. Here's another example of another simulations done by a PhD student in our group, in which they wanted to calculate the critical Micelle concentration of a surfactant in water. This is an ethoxylated surfactant, very much the one that you'll find in your basic toothbrush or hand washing soap. The critical Micelle concentrations, or the concentration at which the surfactants form these beautiful little spheres in which they trap the oil or whatever you want to take out of your hands, are very, very small. They're usually in the order of parts per million, or 10 to the minus 6. So the system sizes that we need to explore are enormous. In this particular case, we needed to talk about more than 1 million atomic centers to try to do this simulation. So this was done particularly in this case in Titan, in the Oak Ridge National Labs supercomputer. And the graph you have on the left-hand side is the best that we can do. On the abscissa, we have the number of nodes in the system. And each node corresponds to 16 processors. So basically, it's one of your high-end workstations is one node. We're talking about scaling this up to 128 in this particular case. And you see that there is a linear scale-up in the power that we can do. The ordinate talks about million atom time steps. So that's one time step for 1 million atoms per second. So the more we get, the better. An interesting slide, and an interesting part of that slide is the red line. The red lines are GPUs. GPUs are graphical processing units, which are cards which are originally designed to play computer games, but basically are very powerful because they have around the order of 2,000 processors, which help speed up computations. So when we activate the GPUs on each one of those nodes, immediately you see a jump in 1 or 2 orders of magnitude in terms of the computational power, especially for the smaller systems, and which is something that we're exploiting now quite a lot. So we need to speed things up. That's the message. So there's several ways of speeding things up, and you can immediately, we've discussed a little bit. One idea is to fudge out some of the detail. And in the bottom part of the slide, you have a picture of water, of bulk water, and then again you see the characteristic red and white signature of how we as modelers draw water with the hydrogens and the oxygens. But you could say water, well, we don't want that much detail. Let's fudge it out into a sphere, which is what's happening when you look at the red spheres in the right-hand side. And one way to do that is, well, let me see if I can reproduce some of the structure of water. In this case, the radial distribution function, or in simple terms, the local density as a function of distance of the different molecules. So if we match our red beads to that radial distribution function, we get a certain functional form for the potential, which then we can later use in our simulations. So by doing that, we solve many of the problems associated with modeling water. Water has long-range electrostatics, has 3 atoms, has hydrogen bonding, and all these things could, in principle, be washed out by a coarse-grained model. Another way of doing more or less the same thing is, instead of looking at structure, we could look at forces. If we have a polymer, for example, like the one drawn here, we could try to match the forces between 2 of these polymers and assign these forces to larger centers of force. Finally, we could we could take a little bit of the idea of of group contributions and think about something like a Lego box, in which for each group of atoms we have a larger atom center, and this atom center has certain characteristics which we fit, in this case, in the case of the Martini force field, they're fitted to water-oil partition coefficients. And with that, we have a table in which we can build the different molecules. All of these coarse graining models have big issues with them. The 3 big issues are representability, robustness, and transferability. Representability is basically it refers to the fact that if we fit to one state point, most likely, in most cases, this information is state dependent. So when we want to use it for other temperatures and other pressures, it won't work. The example of water that I gave you is a classical example where that is an important factor. Another one is the robustness. We want it to be able to not only describe one property, we want to use it to describe thermodynamic properties, we want to use it to describe transport properties, etc. And transferability is what I mentioned in terms of the group contribution model, that the CH3, for example, part of a molecule can be used for in other different molecules all around. So we have, in our group, we have looked at attacking this problem from a completely different point of view. We have used an equation of state, and an equation of state is an analytical closed form expression for the free energy of a fluid. It's used classically in chemical engineering to provide a route to describe the thermophysical properties of a fluid in an analytical way. And for those physicists in the audience, the van der Waals equation of state is a classical antique example of this idea. The equation of state we use, the SAFT equation of state, which stands for Statistical Associating Fluid Theory, links directly the equation of state to an underlying intermolecular potential. So the way that the equation has been derived is to think of molecules and atoms interacting through a potential. And the theory is developed from that potential onwards. So at the end of the day, we have an equation of state which certainly is in terms of macroscopic properties, but the parameters refer to microscopic parameters of the force field that's underlying it. The theory follows very well that underlying Hamiltonian. And in this slide, you see examples of three things on the same slides. The solid line is the equation of state prediction. The dashed lines are the experiments, and you can see here that we are theoreticians, we're not experimentalists, so we just put dashed lines for experiments. And the simulations are seen as open circles. The simulations are done with exactly the same parameters that come out from theory. So the take-home message here is that we can have the same level of precision with the equation of state than we can do with a simulation in fitting experiments. So immediately you can start thinking of flipping the problem around, which we've already done, and basically saying, well, if we have experimental data and we have this equation of state, can we fit these parameters to that experimental data and obtain an intermolecular potential? So now we're actually taking fitted parameters or intermolecular potential, which is actually a very good average of all the thermophysical properties of a given compound. So it represents in a very good averaged way, and in this case, a coarse-grained way, the effective interaction potentials for these systems. And we can use them in molecular simulations. Of course, we could use them to obtain the same properties that the equation of state finds. But more interestingly, we can use it to study interfacial properties, transport properties, mesophases, etc., etc. Examples of how we would do that, or the level of coarse graining, are on the slide. For example, benzene can be modeled, for example, as a single sphere, and we would do that by looking at the properties of benzene and backtracing then the parameters that we would need to model the thermophysical properties of benzene. Those parameters we could use then directly into a simulation. The model can be used again as in a Lego fashion, by putting together different types of molecules to form larger molecules. And we have tested that and with certain success. And by now we have tables and tables of parameters for different chemical moieties or molecules or groups of particles. So let's go back to our asphaltene model, or our asphaltene system. So in this case, this was the atomistic version of our atomistic model, and then we simply build a coarse-grained model out of the table, for example, that I just showed you. And what can we do? Well, the first thing that's obvious is the number of calculations needed for this model decreases substantially. And on the left-hand side, we have the order of 10,000 calculations per each pair. So we have to scale this times n to the square if we want to look at larger systems. On the right-hand side, you have several orders of magnitude less interactions to look at for each pair. So the simulations, those heroic simulations which took us months to do on the large BP supercomputers, can now be done on a worktop on a desktop in matter of hours. So these are the results that I asked Guadalupe Jimenez, one of our postdocs in the group, to do for this talk, and she did them overnight on her computer. You can see that the physics is still there. It's exactly the same one. But the interesting thing is, of course, that the time and length scales that we can now use are incredible. For example, we can look at more complex systems instead of looking at binaries. In this case, we have the bubble point, or the vapor-liquid equilibrium of a 10-component crude oil mixture. We have a simulation and predicted experimental the simulation results, which are complete predictions, as compared to the experimental results, and we find that even to the level of details in the composition, we get it right. We can get interfacial tensions from the system. The graph on the left-hand side shows the predictions from the simulations. The blue dots are our simulations. The red dot is the only experimental data point available. The solid lines are engineering equations of state fit to those data. So those equations of state have fitting parameters, while the blue lines are just simple, the blue dots are just simple predictions. We can also look at more complex systems. For example, in this case, we were looking at a 16-component crude oil. This is a live crude oil for which we had some experimental information. We're talking here about an equivalent of 1 million atoms, in which we have a large number of asphaltene and resin molecules. In this particular snapshot, you can see that the aggregation of the asphaltenes in one part of the simulation, the purple ones. The interesting thing is, again, the size and complexity of the system, which is basically run on a GPU workstation. Not even the largest. This is not the largest that we can do by no means. However, something that probably is already coming to light is the fact that we really are sometimes limited by the tool that we use and the size of what we're looking at. And different problems will probably need to have different microscopes or different instruments to understand what we're seeing. It's my belief that the way forward in modeling is to look at multi-scale modeling, to use more than one tool to study the different parts of different length scales in a coherent way. I might mention, by the way, that this is slightly different than what people call adaptive modeling, in which you run simultaneously two simulations. For example, you could run a continuum simulation and a molecular dynamics simulation at the same time, cross-feeding information for both as the run goes forward. So this is that particularly is an extremely challenging area of research, which is actually being pursued by many people nowadays. I'll give you as an example something that comes out from ICAM 10. In this case, ICAM 10 is interested in producing membranes for purifying water for reverse osmosis applications. The chemical way of producing these polyamide membranes is well known. We start with the two monomers here labeled MPD and TMC, with the names are there on the slide if you want the chemistry. It happens that one of the monomers is usually dissolved, the TMC is usually dissolved in an organic phase, in this case hexane. The other monomer is solvent in an aqueous phase, and of course you know hexane and water will phase separate into two phases. Interestingly enough, MPD is also soluble in the organic phase. So when the two phases are put together, the MPD, which is soluble in the organic phase, permeates or diffuses into the organic phase, where it encounters the TMC, reacts, and forms the membrane. So this is sometimes called interfacial polymerization. The system itself is too complex to study atomistically. There's too many things going on. We have diffusion, we have chemical reaction, we have two phases. We have the effects of the solvent on both sides. We have the evolution of the products of the reaction, etc., etc. So there's no way that we can solve it because the timescales are too distinct, and the size scales are too distinct. I mean, we have the membrane growing, and we have the timescales associated with the chemical reaction. We have the timescales associated with the diffusion, etc., etc. We chose to do some very aggressive coarse graining for this model. In this case, we coarse-grained our models using the SAFT approach I've mentioned before, but we used something called Langevin dynamics. In the case of Langevin dynamics, what we do is not remove the solvent from the problem. In this case, hexane and heptane are doing nothing. Sorry, the organic phase and water are doing nothing. They're just simply laying the ground for these two monomers to come together and react. So what we did was extract the solvent from our problem, take the solvent away. In the equation from Langevin dynamics, which you have in the middle of your slide, you can start recognizing mass times the gradient of the velocity or the acceleration, so that's a force, is equal to, and in the middle of the right-hand side, you see the classical term of the gradient of the force fields. So here we have the force fields amongst our molecules, but we've removed the solvent. So somehow that interaction of the solvent has to be built back in. So we put a friction factor into the equation, to take into account that these molecules would have been slowed down by the effect that these solvent is mediated. But of course, if we put a friction factor and we start eliminating energy from our system, the whole system will eventually come to a standstill. So what we have to do is then add a noise, a white noise, which theoretically can be derived coming from the fluctuation dissipation theorem, and we add some random noise to the system to get back a workable equation. The system cell is based on basically on the experiment. It's a cartoon of the experiment, but basically has the key elements that we think are important for this system. When we run the simulation in a coarse grain model, the first thing that we see is even then with this extremely aggressive coarse graining, it takes a lot of time for things to happen. At 10 nanoseconds of simulation, we just simply have very small clusters of polyamide forming, and these clusters start growing in size, finding other clusters, starting to span the clusters from across a cell, and eventually reach a certain size in which the system then stops growing. Amongst other things, of course, you can recognize that some of the monomers simply can't diffuse after a while because there is a polymer membrane which has formed and physically blocks one of the reservoirs of one of the monomers to the other. And we have found in our simulations that to be in the order of 10 nanometers plus minus a little bit. These are enormous simulations. They take actually weeks and weeks of time just to see this. But the important thing is not that. The important thing for us was actually the atomistic detail of what was happening. And this is what the experimentalists were yelling at us to please explain to us what's happening. So we had to then jump back a scale, take our coarse grain model, and since the coarse grain model is based on a physical representation, a coarse grain representation of a molecule, we can now, in place of those coarse grain model, put back the atomistic model where it was, relax the system, and obtain a fully atomistically detailed model for this. Amongst a few things that we are now testing is, for example, things like the density and the chemical compositions of these membranes, and comparing them to the experiments. And up to now, we have been quite happy with the results we get. The next step forward is to hydrate the molecule. And again, here comes our water or atomistic water molecules again. One of the nice things that we can see from this graph on the right-hand side, you can see a pathway for the water crossing that membrane. It's interesting to note that pathway actually wasn't there initially, and it starts appearing when we hydrate the membrane. So the water is somehow forcing its way through the membrane to go to the other side. So against some conventional wisdom, it's not that the membrane has holes in it and water will go through the holes, but water will somehow creep through the available space and make its way through the available space on this membrane, which in fact is not a rigid membrane, but actually has some flexibility and allows for that to happen. The dimensions of these membranes are commensurate with what has been seen experimentally, and this is a copy of the recent science paper on that topic. So I've hoped with this to convince you that of at least some key ideas of what molecular modeling can do and hopefully what it can't do, which is probably more important. So in spite of the fact that computing power grows exponentially, our appetite for the problems we want to tackle grows side by side. So we're always in the problem that we want more and we want to do more. So we have to be creative. One thing to do is, of course, to sit down and do nothing, because Moore's law just simply states that in 2 years' time we'll have double the computing power that we have today. But even that is probably not enough. In some of these cases, we really don't want to double the computing power. We want to increase it by an order of magnitude, several orders of magnitude. So we have to be a little bit creative about that. It is also unreasonable to expect that atomistic simulations, or DFT, depending on who you talk to, will ever be used to map all types of problems. This is an unrealistic expectation. And we need to, again, find ways to use that information and scale it up so we can look at larger types of problems. And it's also obvious that different types of problems need different types of tools. And again, creativity here becomes interesting. And more importantly, the use of multi-scaled or multiple analytical tools to understand multiple scales is actually probably going to be the key in recent years, in the future years. I put this slide with some further reading for those of you that want to start on the basics of this, which was, as I understood, part of the audience. And I'd like to finish with just a slide acknowledging the people that actually did the work. All the work that you saw here was done by several of these researchers here, and to acknowledge also the generous financial support from EPSRC and ICAM for this work. Okay, thank you very much.